If no one shows up to class next time, this is on the recording, so you'll all hear it. If you don't show up to class and no one's present, I'm not recording shit, period. I don't do this for me, I do it for you. Please show up to class. People on Zoom, you all good. Thank you for being here. But suddenly, like, talking to an empty room really sucks. Someone's got to be in person. All right, we're working on chapter 15. This is on the awesome shit, real life usages in 3D. And recall we had the del operator, which was it was the vector maker. It took a scalar function or a function that had values that scale, non-constant values that scale, and turns it into a vector function. So like in this case, what I've got shown is the scalar function here is phi. And my vector function is v. Okay? So if we have some vector field F, is a conservative vector field. This is pulling a little bit from 15.2, which is motivation for a lot of the stuff we're doing in this chapter. If vector field F is a conservative vector field, wait, hold on. I'm saying this wrong. No, we'll work with that. And phi is a potential function. I said it backwards of what I wanted to say. I know, right?
Like opposite day.
Then F is, this should be the other way around. I'm going to make it the other way around. Let's do this. If F is the gradient of phi, then the vector field F is a conservative vector field, and phi is the potential. Where phi is a potential function. There we go. That's how we're going to word it. We have two new commands. The commands that are operations. We have something called the divergence of F, div F. And what that is you take the del operator and you dot it with F. And we also have curl F. And this is where we do the cross product of the two. Notice this produces another vector. And this produces a scalar. Curl of f is a useful thing. If the curl of f equals 0, then f is a conservative vector field. Which means we can apply the whole f equals the gradient of phi. So 2 new commands. Div f and curl f.
Del being an operator, it kind of looks weird to cross it with F. I know it's.
It does. It does feel weird.
Life's weird.
Right? So let's think about that for a second. You've got like some, let's just do a 2D vector. It's kind of hard to like show this in 3D. So let's say we just have a 2D vector. And it's doing this, but here it's doing that. And then maybe it's flattening out again and it starts going down as we go to the right. And maybe even at some point it turns around. Each of these vectors can be decomposed into like an x component and a y component. And this is what our f is. Like our f at that point is doing this. It's always starting at the base point. The vector is just showing what the path looks like, or the vector field from that path is looking like. So what like doing when we do the curl, because that is ddx, ddy, ddz dotted with the x component, the y component, z component. Maybe not use a hat. Hat means unit vector. This like doing, so when we do it, you're going to have like the ddx of the, maybe writing it as like this. Wait. There we go. The point is this stuff gets applied to it. And so like you're going to have like the first component has ddx of y minus, nope, of z. Hold on. It's dy dz, or dy, nope, that's ddy of the z component minus the ddz of the y component. And that's just the I part. So like, let's think about like what that's trying to say. It's like saying, shit, I don't have a z component here, so it's a little hard to fucking picture. Let's pretend this is y and z. So like, what is the change in the x direction is based on how much is y and z changing? Y component and z component changing. I have a new notation. The lightning, the Harry Potter in a fucking notation. How much is the y component and z component changing with respect to different things? All right, so like it's a little trippy. It's a little hard to wrap your mind around. We'll go into a little bit more detail in a second. Let's get back on topic here. We have four options that combine these. We could do the divergence of the curl of f. So the curl of f is that cross product of the del operator and f. And divergence means take the dot product of that result with the del operator. It turns out this is always zero. It's a scalar. And if we do the curl and then the curl of f, this leads to something fucking like a wonky formula that is a pain in the ass to memorize. And I don't think it's worth your time to memorize unless your actual career has you doing it a lot. Where that del squared is like doing the divergence of a potential function. It's called the Laplacian. And when we use the word operator to go with it, operator is applying to the del squared is called the Laplacian operator part. Just doing that, having that result there is called the Laplacian. Those two are crazy. This is another vector though. And that's where we had curl on the inside. Now let's have div f on the inside. And we've got two ways that can happen. We could take the divergence of it or the curl of it. Now, this is a vector, and this is a scalar. So both of these are trying to do vector multiplication. There's two forms of vector multiplication, the dot product and the cross product. It's trying to do vector multiplication, but not with two vectors. Which this means this is like complete nonsense. This is no. And it's absolutely meaningless. Like you can't do it. So if you want to try to combine it that way, you can't. It doesn't work. There's no math operation for it. But the divergence of where you have the curl on the inside, you can do stuff with the curl because it is a vector. Get rid of that. We don't need that. That was to go with the presentation or the discussion earlier. Those are things we got going on there. And we've got a problem that we're going to work on. So we've got a few things to do. we need to find the divergence of f, the curl of f, show that the divergence of the curl equals 0, and then if f is a conservative function, find the potential function phi. Div f, or divergence of f. I strongly recommend you write this shit down when you do the test, at least this portion. There's no component in Z, but we're going to need it for the curl. So I'm just going to include it. I recommend you do that. And I honestly recommend, even though it'll take you just another 15 seconds, write down the distribution of that stuff on the divergence before taking the derivative. Because this means you understood the last step and you just fucked up the derivative if you get it wrong. But if you just jump straight to the work and it's wrong, and I can't figure out how you got it wrong, you're not getting anything for that fucking part. And that sucks. So being lazy or not trying to write as little as possible, it comes at your own risk. And if there's no work, it's definitely a 0. I'm grading on some work. There's got to be at least something on the fucking page. You can't just drop the answer, because if you just drop the answer, how do I know you're not looking over at fucking Nathan's paper? Nathan recommends not doing that. Nathan's not feeling very confident right now, apparently. All right. What do we get when we do this? That looks like a 2 sine y squared minus 6x. That's my component there. And then plus, we got 2 y's here, so this is going to be a product rule. I got 2x squared cosine y squared. And then if I take the derivative of cosine y squared, I'm just looking at it here, it'll be negative sine y squared, and then times the derivative of the inside is 2y, is going to give me a minus 4x squared y squared sine y squared. And that's divergence of f. We'll talk more about what divergence means on the next problem. Let's take a look at curl. I strongly recommend you write the shit that's the longest things. That way your matrix doesn't look like shit. And if you don't do the matrix and you fuck it up, that's another full loss. Like if you try to shortcut the matrix and don't do the matrix, and just jump to the fucking vector forms of it or the IJK, and you fuck that up, you're not getting any points. That's what curl of f means. Or cross product of the del operator and our function f. So we got I times d dy is 0 minus the derivative with respect to z there. There's no z in it, so that's also 0. And then we do j. We're doing d dx of 0, which is 0, minus, and then we're doing d dz of that. d dz of that is also 0, because there's no 0 or z in it. So far we have no I or J component. And the K component is 4xy cosine y squared minus this is going to become a cosine y squared, and then I've got 2y times 2x is 4xy. And that's also 0. Notice those are the same thing, so those cancel out. This is 0, 0, 0, or the 0 vector. It is significant. It helps us get an idea of what the curl is doing. So whether you've ever actually used a hair curler, I'm sure you've seen what they are. They curl hair. It creates a rotation of hair around the curler or the curling iron.
A lot of hair curling going on.
Right? Curl measures rotation around a point. And like rotation, like axles have rotation. So there's generally an axis of rotation when this happens for each point, but it may not be the same for each different point. So this one right here might have the axis is there, and we're rotating around it like that. And right next door, it could be doing that. And the axis of rotation is like this, which is kind of hard to picture the way I have it going on.
Would the point itself not be the axis? Like,
No, because like the point is just a single point. An axis is a line. So it's kind of a weird thing, but it is. And so when the curl of f is 0, it means there's no rotation. And we call this irrotational. Because the curl of f equals 0, this also tells us that f is a conservative vector field and that it is the gradient of some potential function. So it means that last question has some work to it that we're going to have to do. We've done the divergence, we've done the curl. It says show that the divergence of the curl equals 0. This may be trivial on this problem, but I'm going to show it anyways. Because it's not always trivial. And the more you see it, the better it is. The curl of f was 0, 0, 0, which means we get 0 plus 0 plus 0 is 0. All right, we did show that this was a conservative vector field. So our next step is to find the potential function. And the easiest way of doing this is to write out what this means. We have f of x, y, z, which is f in the x direction. I should say component or comp, comma, f in the y component, f in the z component. That should equal ddx, ddy, ddz of phi. So in general, working that out, the x component of d phi dx, the y component is d phi dy, and the z component is d phi dz. And that's what I wanted to put. I fucking wrote that crazy.
This is still in relation to the original function, right?
Yes. Which means if we look at our original function here, the x component was 2x sine y squared minus 3x squared. That should equal d phi dx. And then I'm not going to do the z component because there was no z component. It was 0, 2x squared y cosine y squared plus 1 should equal d phi dy. And our goal is to find phi of xy. If I have d phi dx, how can I get phi? Or if I have d phi dy, how can I get phi? Integrate. So what we can do is integrate. Integrate with respect to the letter that's on bottom. And if we're doing it on the right, we have to do it on the left. We could do this over here by doing d dy. Let's start with the dx. If I integrate that with respect to x, I have x squared sine y squared minus x cubed plus a constant. But the constant with respect to x, that's what the constant means. It's a constant with respect to x. Why I'm pointing that out is if we had like y squared or y cubed all by itself and we did ddx of that, that's going to be 0. Just the same way ddx of a constant is 0. So this constant with respect to x could be some function of y. So phi of xy should equal x squared sine y squared minus x cubed plus some function of y. It's deep. Now, one way of doing this is also integrating the other one, or when you have 3 of them, integrating all 3 and just finding the overlap. But I think there's a little bit of an easier way of doing this. If I take the derivative with respect to y of this bad boy, I get g phi dy on the left side. On the right side, I get 2x squared y cosine y squared. We're doing the derivative with respect to y. The x cubed goes away, and I have g prime of y. Make sure that makes sense to you. My Calc 1 class is looking at antiderivatives for the first time today. It's just working backwards from derivatives. Hopefully they find it easy. All right. This d phi dy is equal to that, but it should also equal this portion here before I put the integral in. In fact, I'm going to get rid of the integral for a second. Yeah, let me get rid of the integral. So we had a d phi dy up above. This d phi dy is the same as that d phi dy. Because they're both the same potential function, which means this should equal that. Does that track? Does that make sense? If we had a potential function? Which means if those two are equal or the same, if they're the same, that means they're equal. And if they're equal, it means we can set them next to each other with an equality sign, and then we can figure out what g prime of y has to be. Does that make sense? Because the d phi dy was what we were getting, this up here was given based on conservative vector field. Curl of f equaling 0. And this one was developed taking derivative with respect to y. That we calculated. But they are the same phi. Which means if we put them together, g prime of y has to equal 1. Because this term here is the same on both sides, so we can just subtract them out on both sides. And if I integrate this with respect to dy, we get g of y equals y plus some constant.
Respect to X?
No. Yeah, with respect to y. Because we're trying to get maybe a better way of writing this is dg dy. Let's do that here. Shit. Or highlight back in. I said g prime of y, but and maybe that should be a hard d because g was not a partial, or it was not a function of two variables, so it should be a hard g. A hard d. That should be a hard d.
Can I just ask a point of clarification on like vocabulary
Yeah,
where we, the, dp, dy, um, from the original function of f, that's the y component of our original function.
yes.
And we're saying that it's equal to d phi dy, which is given based on,
Taking the derivative of the phi we calculated here. Oop. We calculated a phi here,
yeah.
gives us that one. So that's a d phi dy there, but we had d phi dy right here also, which was the y component of f. And they should be the same. Putting it all together, we want to have what phi is. I'm looking for final form here at the end. Phi of xy in this case, in some cases we'll have a z, but in this one we don't. X squared sine y squared minus x cubed. And then our g of y was y plus c. Look good? All right. Let's find the divergence curl of this stuff. Same questions as the last one. We'll start with div f. If you want to jump straight to writing it in this form without showing the two vectors multiplied, that would show that you know what you're doing and might save you a step on tests. But for the sake of completeness, for people that don't recall what this is doing, we're doing that. If I do that, I have ddx of 5y squared z is 0. ddy of negative 3x squared z cubed is 0. And ddz of 2x cubed y is 0. The divergence of f equals 0. This gives us a fun time to talk about what divergence means. Let's talk about a physical representation of divergence. And you can very much think of it like, remember convergence and divergence in Calc 2? Convergence closed in on a number, divergence went away from a number or a value. Convergence approached a value, divergence went away from. That's the same thing here. At a point, let's write down like 3 different points and show 3 different scenarios. Divergence in itself is something going away from a point. This is when divergence of f is greater than 0. And this tends to be used a lot in fluid flow, like water, oil, air, plasma, fuck, if you want to be crazy, you could put lava. Lava is technically has fluidic properties. So if there's a flow away from a point, kind of like Big Bang, shit just came from a point and then a whole bunch of shit came out of it. We call this in the physical representation a source. Like a source of flow. If instead everything is just moving into it and nothing's coming out, this is kind of like almost like converging to the point. But we don't use that in terms of physical stuff. This is just the divergence is negative. And if water approaches the point, but it never leaves the point, it's acting like either like a black hole or like a sink in real world. It's like a drain. And we call this a sink. Sources and sinks. Our final scenario is when div f equals 0. That could mean no flow at all in any direction, but usually isn't the case when you're talking about fluid shit. That's just stagnant water and completely fucking uninteresting. You're not doing vector field shit on a fucking pool of water that isn't moving. So this tends to be when the same amount of water that's going in is the same amount of water that's coming out. Kind of like what happens in a pipe. And if the same amount of matter or water is going in as the same amount that's going out, it means it's not getting squished together. Like if I tried to pour water into my cup, eventually it's going to overflow. But if it didn't, if I could just keep pouring water and it just kept going in there, it would mean the water would keep getting compressed tighter and tighter and tighter. You don't picture that with a cup, but like a pressurized can of air has when you the things you inflate balloons with, it's a pressurized thing of air. The dentist's office has pressurized nitrogen, laughing gas, to knock your ass out when they need to do fucking mouth surgery. You can compress the air, but in this case, we cannot compress the water. We call this incompressible. Incompressible fluid. I'm going to say 4 fluids. The idea that divergence of F equaling 0 for something else is kind of hard to explain. Like taking fucking rock and trying to pressurize it. It's not like, I guess fuck it. We'll just call it incompressible. I guess you can compress some shit like carbon compresses to diamonds, right? All right, so we got a couple like curl of F was rotation. Yeah.
For the divergence being 0, what if it was like circular around, or can it not be like that?
If the flow is going around it, but nothing is going into it and nothing's going out of it, it's still 0. That's doing the case where we just have the point and there's no. You're talking about like doing this, but there's no flow into or out of. Is the same thing. Kind of like the moon circling the planet, a planet. It's going around it, but it doesn't go in. It's not, the planet is not a source or a sink of fucking moon in general. All right, let's do a curl F and keep going here. Got a few minutes left. I'm gonna do ddy of 2x cubed y gives me 2x cubed. Minus ddx of negative, minus a negative will give me a plus 6xz cubed. Nope, that should be a z. I wrote fucking, either way, it's still a positive. 9x squared, z squared. And then I have minus j hat of ddx, or ddx of 2x cubed y is 6x squared y. And then I have minus ddz of 5y squared is just 5y squared. Or 5y squared z, sorry. And then I have plus k hat of ddx of negative 3x squared y cubed, or z cubed is negative 6x z cubed. Then we have minus ddy of 5y squared z is 10yz. And that's my curl of f. This is not zero everywhere, which means f is not a gradient of some potential function. We wanted to show divergence of the curl of f was 0, which means doing ddx of 2x cubed plus 9x squared z squared plus ddy of negative 6x squared y plus 5y squared. I'm distributing the negative there. And then plus ddz of negative 6xz cubed minus 10yz. Hopefully I didn't fuck any of that up and we actually have something here that makes sense. Sign mistakes will get you on this shit real quick. We have 6x squared plus 18xz squared. Then I have minus 6x squared plus 10y. And then I have minus 18xz squared minus 10y. That cancels that. This cancels this. And that cancels that. So that does equal 0. And the last thing, since f was not the gradient of some potential function, there's no phi to find. Or no potential function to find. And that's it for the official class. I'm actually going to do problem number 3 for the recording. If you got time, stick around for it. We're going to assume that F is a conservative vector field. We could prove it by doing that. Proof is doing this. But this should be the same thing as d phi dx, d phi dy, d phi dz. That's my gradient of phi. That's that. And that should equal my f, which is x over the square root of x squared plus y squared plus z squared. Y over that. And z over that.
Thanks for salt and pepper chips.
Sure. I'll take them. Thank you.
Yeah, I never did John yet.
I'll say it all the time. Oh, you know that coffee, the little content, was that cold brew or regular? I had some like when I got it, but instant, that's what I meant.
Finally, the
Neat.
ones that I brought were like editor samples, so that's why it was
Right.
given away, but we've since brought to production our instant coffee.
Nice.
More work for me.
My wife saw it and she was like, I still had some left and I haven't had some in a while and I forgot. Well, I'm like, was it I was making an instant or not?
Pretty good. I said ours is better. I'm not just saying that.
Nice. So that's my d phi dx. That's my d phi dy. That's my d phi dz. And phi is some function of x, y, z.
Got coffee to make.
Have a good day.
You want
All right, so we're gonna take d phi dx and integrate it with respect to x, which means integrating that with respect to x. Not the most fun thing. Do a quick U sub on the inside. Have a good one.
Pretty sure we're not on 15, so this is the previous class.
Yeah, I'm still recording a video here, so it's okay. There's a couple people on Zoom still. So we got that, which makes this integral. I've got phi of x, y, z when I integrate the left side. This is doing the integral of 1/2 1 over square root of u, which would be u to the negative 1/2. We do that integral, and we go up a power, which is 1/2, divide by the power, and we just have u to the 1/2 plus some constant. Now, when we convert back to phi, or x, u was, or we have 1/2 square, or 1/2 u, square root of u, which is square root of x squared plus y squared plus z squared. And our constant now is the constant with respect to y and z. Because this was a function with 3 variables. So maybe I'll write g of yz. Like we did with the previous one. In fact, I'm going to copy that because I want to leave that alone. Like we did in the previous problem, what we did next was we took the derivative of this with respect to y. So we get d phi dy equals, this is x squared plus y squared plus z squared to the 1/2, which means with respect to y will give us x squared plus y squared plus z squared to the negative 1/2 times 2y. And I got to put a 1/2 out front. So that puts a 2 down here, which means those 2's cancel. And we have that. Then we have d dy of g. And that should equal this part here. Should equal, since it's d phi dy, it should equal our d phi dy up here. Which means we're going to set it equal to that. And we can see this is present on both sides. So if I subtract it out, I have d dy of g of yz equals 0. Now to find g, we'll integrate with respect to y. And we get g of yz equals a constant with respect to z. So let's call it h of z. So there was no y component. So I'm going to take that, go back up top, plug that in. We're at this point now. Is that making sense, Ashley and Elvis? I hope so. We got one last step. We're almost there. Take the derivative with respect to z. We get d phi dz. This is doing the same thing as respect to y, but it just gives us a z on top. And we have h prime of z. And that should equal our d phi dz up here. Which means h prime of z equals 0. And if we integrate that with respect to z, we get h of z is just a constant. We'll take that, we'll plug that in up here. And our final answer is phi of xyz is just the square root of x squared plus y squared plus z squared. Plus a constant. Now, in this case, the gy of z turns to h of z, turns to just a constant. It was just a constant. Sometimes, like in problems on the homework and other, like when we do tomorrow, 15.2, Each of those will have like a y component and then a z component. So it's not always just giving us a constant, but in this case it was. And that'll be it for the video. I'm going to hit stop record and then I'll leave this up.